Now let me lead off. Noel was the one that made up this title. So I had, his software broken or something really eloquent like that. But can you tell the difference between, tell me what the difference is between a used car salesman and a software development manager? The used car salesman knows that he's lying. Okay? So what we're going to talk about today is if everybody's been talking about being the taillights, Mars 98 was a taillight, NEAR is a taillight, then everybody talking about lessons learned, then I want you to regard me as a prophet, okay? Because I'm going to tell you about something that's coming your way. And I'll try to do it in a way that gets you to the bar here in 10 or 15 minutes. We've already talked about Mars exploration program. Noel has set the stage well. The Maven people are all shaking at this time. I really want to talk about real-time embedded systems, aka software. You've already seen this picture, at least in previous presentations. This is the Mars exploration program kind of plan that moved us all the way from the early missions over here in Global Surveyor and all the way out to where we are waiting for MSL right now. You'll notice that Mars 98 is conspicuously missing from this particular view. It was actually stricken from all obelisks and everything around there. But it occurred right in this period of time, okay? And this just sets the stage for it. Mars, this is a chart, Noel, that I stole from you years ago and have been keeping it updated, keeping score. So it's a hard place to go and actually practice discovery missions, scout missions, whatever. And when you really mess up, then you get written up in, I'm written up in chapter 10, thanks Noel. And when science goes wrong, the dark side of discovery. And I told my mom I always wanted to be famous, but I didn't think I'd be infamous. So, and Noel, I appreciate you taking credit for all that, but over beers, I'd tell everybody else that the technical team let us down also, and present company included. So there was plenty of blame to go around. The thing that has become apparent is trying to design for failure tolerance. And these are some pictures that Ed Sedevy will recognize that kind of came out of the Phoenix mission. One of the things we found when we tried to recover Mars Polar Lander and went to Phoenix and turned the whole JPL Lockheed Martin dynamo loose on that problem in Langley and all the other groups, was we discovered other ways that the vehicle could have failed back in 1999. But the most disturbing part of it all was in the thousands of Monte Carlo tests that we ran. We began to discover interactions of even the environment itself during Mars descent with, say, data parameters that earn an FPGA and then hence upward all the way to flight software to create failures that we never thought we could imagine. And in fact, that's the whole key, is that your FMEA and your fault tree analysis and everything you have up here is only as good as your failure to imagine. And so we're seeing all kinds of things happening now in modern spacecraft development that I'd like to talk about. We're experiencing all kinds of software issues. If you recall the famous programs, they're huge. I guess they even make, when Gus was talking about Viking at 5,000 or 6,000 people, let's talk about SIBRs or INPOs or those are easily that size. And you've heard of all kinds of massive delays, Nunn-McCurdy hearings. And when we called into these things, software is to blame. That's where everything has happened. There are also hardware problems. We haven't gotten beyond those. But we talk about this marching army effect. Software at the end is the only thing that can both make everything happen and stop everything. You rarely have a hardware problem other than avionics issues that I'll talk about in a few minutes that can stop a program. So you end up with major delay, potentially, and in a planetary window, which you're all working towards, the New Frontiers folk in Discovery, you have to meet that window. Only one mission recently that I can think of escaped that window and got booted to 2011. You'll know which one I'm talking about. Well, 3 years ago, we held this fancy, this is a moniker within the company called Kaizen event. It's actually industry-wide, but we held this event because a major program had software delays. It was costing billions of dollars, overrun to the program. And so they called in all of the smart people from over the corporation to come in and analyze it. And supposedly when you come into these kind of events and apply these Japanese kind of technique, you're going to find when you come out of it that there's a bunch of symptoms, but there's only a few root causes. But we came out of this thing and, let me see if it's my next slide. We came out with 130 root causes to the software issues associated with this single program, which was insane. We all kind of went away thinking, well, the Kaizen process must be broken. I came away confused, and even when we reconvened the group again, and we're talking maybe 40, 50 people all coming back together again and doing a multi-day look at it, we still couldn't peel back the onion. We ended up with still over 100 root causes. How could these on one program all be completely independent? But we noticed a pattern. Even though we couldn't find a definitive link against all of them, all the problems that were listed, all 130, surrounded the issue of interfaces. Interfaces to star cameras, to IMUs, to mechanisms, to any kind of gadget that was out there, even within subsystems. So it all went around interfaces. So we started thinking hard about this, and I did a little study and kind of in history to remind myself of where we might have came from, and going all the way back and Gussel like this, all the way back to Apollo guidance computer, and looking at that and comparing it to a modern manned vehicle, the Orion crew vehicle, I was able to prove what we had already pretty much known, which is software, which used to only interface with a few things like an actuator and a pilot, aka astronaut, now interfaces with everything. This is an N-squared diagram that you've seen used in system engineering before, and what it shows is that we interface with everything except structure. So software is everywhere, and its interfaces are multitudinous. So it kind of proves the obvious. I think all of us that have built anything recently know this, but it gets more insidious, okay? When I went back and looked at Gemini, it was easy to find out data about this. I go back and I find, this 13 to 36,000 words of assembly language, okay? And the Apollo guidance computer, we talked about that a second ago. I talked about the astronauts providing input. And so I, compared Apollo to Orion and found that Orion is at about 1 million lines of code right now, and that's really reduced instruction set code that, in the form of C or C++, not even assembly language. So there's no real way to actually compare 36,000 lines to 1 million. And you might say, well, why has this happened? Is it just because they can? What we concluded in our study here, and this is written up in a paper that I have listed on the front, which is actually in the Ask magazine from, I think, last spring, is that the modern spacecraft we fly now, including any of them that you're building or you're going to use on New Frontiers, does not resemble the space. It only resembles in physical form the spacecraft of 10 or 15 years ago, and I'm going to prove that here in a second by just looking at generations within Lockheed Martin. There's a couple things that bother me. One is object-oriented code did create an inflation of its own, but secondly is this growth and parameterization, which is all the data elements that used to be embedded in the small groups of code that we had. You remember the 1024 RAM that you were allowed to have, KRAM. Now you've got huge lines of code. We've got hundreds of thousands of parameters now, data elements that have been pulled out of the code and they actually exist in files that we have to uplink to the spacecraft, which can radically change the behavior of the code. In fact, it's like writing code all over again. And then something that adds on to this and compounds it is the use of firmware, which you might call software, that are resonant in FPGAs and ASICs and things like that. And I'm going to bring this connection in a little bit further. It's now brought software to the forefront of all the development issues, which is why it gets blamed late in the program. But I wanted to go look 10 years ago just to see if I could really put some history behind this. So I went to Mars Global Surveyor and then the Mars Reconnaissance Orbiter, and I looked at the code growth in logical slot from 113 to 250,000 lines on MRO. But this doesn't even include all the firmware, which is resident in FPGAs, which could easily be millions. So we're talking about an absolute explosion. And MGS did not have that, did not have much firmware on it compared to MRO. If we look at Stardust, which would really have been the faster, better, cheaper era that Noel was talking about, and then Mars Odyssey, even only one generation later, we see that the databases went from 25,000 to 125,000 to MRO. So this is comparing this era to MRO. And the worst part of it was that Mars Odyssey only had a few thousand of those parameters that could be considered mission critical that could bring the end to the mission. By the time we get to MRO, we're over 20,000. So we're seeing, and it's combinations of these parameters. If they're set at the wrong level at the wrong time, will bring down the vehicle. So what I'm trying to get you to understand is that you can think hardware all the day long about things that can go wrong there, but now we have this intimate relationship between software and parameters and hardware. The other thing that Noel talked about was economy of the Mars 98 time frame. Well, now we actually, the code that's being flown for all these new frontier missions is really just a growth of code that we used on MRO that we actually can use different parameters to make the code do different things. So we're now programming with parameters. And it's not just in NASA. I went and did a survey. I found that in military aircraft, the F-22, which has been in the news a lot, has 2.5 million lines of code. That's actual code, not just firmware. If it follows the spacecraft trend, then the firmware could be measured in trillions of lines. The GM car, I don't know since they became the government motor corporation whether this is still true, but they expected to be at 100 million lines of code in 2010, and that's with 70 to 100 microprocessors distributed throughout their bus, okay? And then it gets much more difficult. We started thinking about the electronics revolution because I cannot decouple what's happening in software from avionics. And so I began looking at 1990 spacecraft, many of which you've heard of today, and the black boxes that were in the command and data handling system. Looking at new packaging techniques that had increased the physical and functional density of the circuit card assembly, as well as the individual EEE parts now getting down to feature sizes that are measured in nanometers. So what I found was that on MGS we had 22 boxes that made up the command and data handling system that became one box on Stardust and Mars Odyssey due to these techniques. And if you think about that for a second, on MGS, when you were the system integrator, you're the PI leading this mission, you thought you were integrating systems when you connected boxes together. So you bought boxes, connected them together, and tested them. Now these boxes are all being connected together when we have one box or cards put together in a lab, or when an FPGA is programmed by a programmer. They're doing system integration at that time. I've talked about the ASICs and FPGAs. So when you hold a card from a modern CNDH, you're holding 22 black boxes of the past. We essentially have had a system onto a chip. And yet I still have 20 boxes. Have you counted your boxes? So what's going on? How come you can have this implosion and yet still have the same number of boxes? So we'd say that software went from a subsystem to a system. Ed, I borrowed a picture of your vehicle. This is not descending to Mars, but inside the test chamber. Together, what I maintain, and this is the profit part of this, that avionics and software have become the system. So, and I apologize to mechanical engineers. Propulsion engineers are liars also, just like the software people. To all of them, they're all merely support for the system. And this is the one that's going to kill you. Now, this is the one that is going to drive your costs. This is the one that you're going to have the most difficult time saying that you've actually V&V'd. The implication to space mission development is absolutely astounding right now. Common cause or common mode failure, which is something we always ignored, in the past is now upon us. Even in low-tech stuff like the 6 computers on board ISS, they had a condensation issue, if you recall, and they lost 4 of the 6 and lost control of the space station. Well, that particular failure mode wasn't on anybody's FMEA or fault tree. And yet it didn't prevent it from happening, so it's a failure of imagination. Well, on Orion, we've been looking at, and we've experienced on other spacecraft, common cause failure associated with these new electronics and their susceptibility to low-dose radiation. So when you say you have 2 or 3 of the same thing, or even a backup flight computer, if it contains the same double EEPROM in it, it could actually, you could lose the whole mission. And there's and within our company, there are activities going on right now to figure out how to actually communicate to a spacecraft that has lost all of its computers. So one of the things I wanted you to think about in the design of your mission, and certainly I am for GOES-R and for others, is maximally dissimilar safe hold. That is something that is, it might even be old school, like closing the sun sensor around an analog device, which has been done. We have lots of examples of that in past design. But you need to think about that, because claiming that you're okay just because you have redundancy may not be the case anymore, because the game is changing on you. One of the things I didn't point out is we don't push the electronics design anymore. We actually receive it from the commercial industry, right? We upgrade parts. We can't control feature sizes. We can't control complexity. It's all being foisted upon us. And if you think you can avoid it by buying a whole ton of parts, you're wrong. It'll only last, for 1 generation, and then you're going to have to deal with it. We've already talked about MCO and MPL. I think that my message here is that because of this new complexity, there are thousands of ways to fail, and only a few have been explored. So we can get together here and tell each other about all the ones that have happened, and you can shake your head and say, that'll never happen again. But that's only the ones you know about. This is a statement I made here that I feel like we're actually in a more risky situation now than we were before, and it's only getting worse as Moore's law is followed in electronics and in software. This should be a chart that I can scare you with. A lot of people think that requirements verification takes place at the spacecraft level, or at worst within a hardware-in-the-loop simulation. This data, Ed, I stole from Phoenix. And on Phoenix, it shows us that 90% of all the requirements buy-off was done on an all-software test bed that we call SoftSim, or in similar devices at JPL, and then at unit test itself. This pyramid of buy-off and how little is done at the spacecraft is indicative of the same thing I'm telling you, which is the perceptibility that you need in order to buy requirements off in millions of lines of code has to be done here. You might have enough money in an infinite budget to make a hardware-in-the-loop do it, but you'll never have enough time at the spacecraft, and you'll never be able to inject all the faults you need to, or to put the fly wires on the vehicle in order to give you that perceptibility. So Test Like You Fly has a huge problem now, and you better make sure that you certify these test beds because you're buying most of the mission off with it. So my job is to be a herald to say that we need to transform project and system engineering. To do that, we need to recruit more people from the software and avionics background in there. I think future chief engineers will have that background and know less, perhaps, about hardware. We need new techniques and tools. I don't know what those are yet. I'm trying to invent them on the mission that I've been assigned to now to manage these numerous interfaces. I've now got thousands of interfaces to go manage, and if I use traditional techniques like ICDs, it's not going to work, interface control documents. And that was the point of this one. We talked about early V&V. I can't remember who brought it up. Was it you, Ed? Or others have mentioned it too. Here I'm poking on the validation. If you have lots of these interfaces, the sooner that you can prove that the interface does what you want it to, then the interface will work later when it comes together. So early exchange of simulators, emulators, having these all software and hardware-in-the-loop test beds to go prove both the digital and the analog interface is important. And I think that if you ignore all this, then the flight software changes are going to be the only way to make the launch, and you're going to be another SBIRS or NPOS, or you pick your favorite marching army, and will fail. So Bottom line, I claim that the game has changed and it's changing around us. The symptoms are all there. It first occurred null on Mars 98, even at those low levels of software and everything. Both of those errors were actually software errors. Okay, even though we failed to find them in test, in one case, both of them were software errors. I've already said this, you got systems on a chip, you need to be careful. Well, let me bring this up. If you're going to be a successful system integrator or a PI here, and you're going to take the avionics that constitute your system and say it's a commodity and I'm going to go buy it from somebody, a third party, you don't own the IP that's in there, you're not going to know how it really works. They did the system integration for you. All you're doing is plug in 22 boxes that are in one box together in the rest of your system and claiming you're doing integration. So you need to be very careful about buying somebody else's CNDH that you don't know what's actually in there. And I guess that was my last point. So I put references at the back. One of them is the Ask magazine. I want to thank Don Cohen and others who let me use this as a forum to make these discussions. And there's some other stuff out here. This is a good study, good thing that was actually led by somebody from JPL on flight software complexity. It's good reading also. Anyhow, with that, I don't want to hold up our move. So thank you very much.